Welcome to this video. In this video, we're going to solve a coordinated equation. Find median in a data stream. Find median in a data stream. So, in this video, we're going to be solving this question. This is very important coordinated equations. Now, let's talk about how to solve this problem. Let's assume we have a stream. We have a flow of integers 1, 2, 3, 4, 5, 6. What is the median of this stream? Can you tell me what is the median? We saw the length is an even number. So median is the average of the middle two elements. So median is 3.5. What is the median of this stream? 1, 2, 3, 4, 5. Can you tell me the median? Since the length of this flow of integers is an odd number, so median is the middle number. So this is the median. Alright, so I hope you have understood how to find out median. Now let's talk about how to solve this problem. Let's assume in our flow first we have 1, then 2, then 3. Okay. This is obvious. We can find out median easily because this number is in sorted order. That's right. What if we have this flow 4, 5, 6? Okay, this is not difficult for you to find out median of this string. You can get the middle two number and you can find out the average of them. So you'll get the median. But my question is, if we have this flow, first 5, 2, 4, 1, 6, then 3. How do you find out the median? Can you tell me how you can find out the median of this stream? You might say, okay, Barik, I can just sort it in ascending order. Okay, let's do it. If we sort it, what do you get? We get 1, 2, 3, 4, 5, 6. That's nice. Now we can just get the average of the middle element. That's correct. But the time complexity for this approach is in log n time complexity. If we add one more element here, let's assume we added here minus 10. Now we have to do, in order to find out median in this stream, we have to first sort it. So the sorting operation will take time complexity of n log n. Is this efficient solution? If we have million of median find operations after adding some number of elements, we'll always have n log n time complexity. That is not good. So what we can do? Can we do it better? Obviously can. So what do we do? First we took 5. Okay, let's put at the first position. Then we took 2. We're going to insert 2 right here. 4. Now we see 4 is not in its position, so we can just move it in its perfect position. We can do it in O of n time. We can sort it in O of n times, since we are adding one element at a time in our stream. Is this efficient? This is efficient than linear logarithmic, but still this is not an efficient solution. Can you improve it? Yes, obviously we can improve it. We can improve it from linear to a logarithmic time complexity. Let's see how. We know we can solve this problem in linear time complexity. The median finding operation in the data stream will take linear time complexity. Now let's reduce this time complexity from linear to logarithmic. So how we can improve this linear time complexity to logarithmic time complexity? In order to solve this problem in logarithmic time complexity, we are going to use heap data structure. We're going to use two heap data structure, min heap and max heap. So to solve this problem, we need two data structure, min heap and max heap. Now let's see how to solve this problem using heap data structure efficiently. Let's assume we have this flow of integers. Our job is to find out the median from this stream in logarithmic time complexity. Let's create here two data structure, min heap and max heap. This is our min heap and this is our max heap data structure. So min heap and max heap. This is going to be a little bit tricky. I would say please pay your full attention to this video right now. Now what we are going to do, since this is our stream, in our stream first we have the number 5. So first our number 5. Now what we're going to do, where we're going to store this number 5, in min heap or in max heap? Can you tell me? Okay, don't worry. Before understanding where to insert this number, first try to understand how we're going to approach this problem using heap data structure. First, let's talk about the intuition behind this algorithm. So here we have 1, 2, 3, 4, 5. Let's add one more number, 6. Our job is to find out median. Okay, our job is to find out median. Now here what we're going to do, we're going to partition this array into two halves. We're going to partition this array into two parts. In our first part, we're going to take this first three element, 1, 2, and 3. In our second part, we're going to take this three element 4, 5, 6. 4, 5, 6. Okay, we're going to store in our right half. We're going to store in our right half 4, 5, 6, and in the left half 1, 2, 3. Why we're doing this? Okay, this is very important to understand how we're going to apply our min heap and max heap data structure. Let's swap this name. Let's say this is our max heap and this is our min heap. So it will be easy for your brain to understand or to sync this algorithm easily. Since we saw the length of this array, the length of this array is an even number. For even number, we know that the median is the average of middle two element. Now we have this and this. Now what we're going to do, we're going to pick the minimum. We're going to pick the minimum from the right and maximum from the left. And we're going to find out the average of them. So what I will get then, 3 plus 4 divided 2 equals to 3.5. This is our median, right? So from the right part, we're going to store the value in our min heap data structure. So what do we get? 4, 5, 6. From the left part, we're going to store the element in our max heap data structure. So we get 1, 2, and 3. Did you understand what we're doing here? We are partitioning our array and we're storing the maximum element, the element on the right part in min heap and the element on the left part on max heap. Why we're doing this? Because our job is to find out the median. So if we store the minimum possible element, then from here max heap we'll get the max 3, and from here we'll get the minimum from min heap. From max heap data structure, we know that if we give us the first element from the data structure, if we call pick function or pull function, or if we say method, then from max heap it will gives us the highest value first, and from min heap it will gives us the minimum, the lowest value first. Okay, so we can find out median by taking the peak element from here, that is 3, peak element from here 4, and if we average we'll get 3.5. This is the case for the length of string even number. If the length of the string even number, it will work exactly like this. Now if we have here one more element, let's say we have here 7. Now what we're going to do, in our left partition we will have one element less than the right partition. So on the right partition we will have 7, and in this case we know that the median is the middle element. Since you are storing one more element on the right parts, so our median is the minimum from this part. Is that correct? This is kind of a self-explanatory. This is not that much difficult. So this is a single logic. If we have sorted out all the elements on the left, these elements are less than all the elements we have on the right parts. So if we take the minimum element from here, we'll get the median. So median is 4. If we just add here 7, so for this problem our max heap will hold 1, 2, 3, min heap hold 4, 5, 6, 7. I hope you get the idea, and this is what we're going to do. Now you might ask, hey Barik, you are doing it precisely. That's okay. You're dealing with a sorted string. That is not difficult. We don't need heap data structure to solve this, because we know we can find out the median since the data is sorted. But our data can be unsorted. You're absolutely right. Now let's see how to handle this kind of case. We don't have to sort it. Our given stream don't have to be in sorted order. It can be in any order. It can be in sorted order. It can be in unsorted order as well. Now let's see how we're gonna apply the same logic here. Alright, let me erase everything from here. Okay, now let's handle this string. We have in this string 5, 2, 3, 6, 1, 4 in unsorted order. So if we insert in our max heap, what we will have? We will have 1, 2, 3. In our min heap, we will have 4, 5, and 6. 4, 5, and 6. Since the length is an even number, we can get the peak element from here and from here, and we will average them. 3 plus 4 divided by 2 equals to 3.5. I hope you are understanding. If you have any problems, you can comment in this video. Now, how we're going to partition this? This is unsorted, this is sorted, this is easy, this is not difficult, right? So how we're going to insert in our max heap 1, 2, 3, the minimum element in a partition, on the left partition, on the right partition. From the left partition will store in max heap, from the right partition will store in the min heap. The size of max heap and min heap can be the same. Also, the size of min heap can be greater than max. In that case, we will have one more element in the min heap than max heap. Okay, let's see how to do this. If we can store here the 3 element here and the 3 element here, 4, 5, 6, then we're done with this problem. Are you agree with me? Okay, let's do it. You may think, hey Barik, if we have here one more element, let's say minus 10. Alright, so let me erase everything here. You might ask, let's insert here minus 10. So what will be in our partitions? That's a nice question. Here we will have -10 and we'll have 3 right here. In that case, this 3 will be the peak element from min heap, will be our median. Okay, we'll handle this. Let's see how. So now we're going to implement, we're going to talk about our core logic, how we can store here and here our element by partitioning. The minimum element in our max heap, maximum element in our min heap. So you can find out the minimum from the right and maximum from the left. So we can easily find out the median. This is kind of a self-explanatory. Alright. First we have 5. Now we're going to insert straightly in our min heap data structure. So in our min heap we have 5. So first we took the first element from our stream, inserted in our min heap. We don't know still the size of min heap and max heap. We just inserted this one element in our min heap and max heap. Okay? Now we're going to pick the minimum element from here. Let's remove the minimum element and let's put it back here. Okay? Now we're going to check if the size of min heap is less than max heap. Then what we are going to do? If we see the size of min heap is less than max heap, we're going to remove the max element from max heap and we're going to store it in our min heap. Okay, it's kind of intimidating. Just let me go through this. Let's put it back here. 5. So our first element stay in this heap data structure. Let's move forward. This is kind of intimidating. I know that. When I was learning this algorithm, I was feeling the same. So if you feel that, no problem. Let's insert 2 in our min heap data structure right here. Now what I'm going to do, we're going to pick the minimum element from here, which is 2. Let's put it back here. Now we see that the size of min heap is not less than max heap. So we'll do nothing. We are done. So up until this point, we have processed these 2 elements. Now if I ask you, please tell me the median. Can you tell me the median? That is nice for this stream. That is the average of the peak element from here and here. So 2 plus 5 equals 2 7 divided 2 equals to 3.5. Okay. Now let's move forward. This is our next element. Let's insert in our min heap data structure. Let's remove the minimum from here, 3. Let's put it back in our max heap. So 3. We see size of min heap is less than max heap. So let's pull or remove the peak element, which is 3, and let's put it back here. Now if I ask you, please tell me the median. What is the median in here? Median is 3. We can find out that in constant time. So find median. This will take constant time complexity. Alright? And inserting in order to insert in our data structure, we have to store our data from our stream in our data structure. That will take time complexity. Insert in order to insert in a heap data structure, it takes time complexity O of log n. This is for heapify. For heapify algorithm that we have in the min heap and max heap data structure. When we inserted the element in our min heap, we'll have the minimum element first. It will create a tree data structure inside. It will do heapify. If we insert the element, it will store at the peak, at the first position or in the root position. We'll have the minimum possible element. And for max heap, we'll have the maximum, the highest element in the root. I'm not going to here heapify. Maybe this is not the right pronunciation. Anyway, so heapify will take logarithmic time complexity. So if we say what is the median? Median is 3. The minimum from the right. Okay. Let's move forward. 6. Let's insert here. What is the minimum? 3. Let's remove. Let's put it back here. Now we see the size of min heap is not less than this. So we'll do nothing. Let's move forward. 1. Let's insert in our min heap. Let's remove the minimum. Minimum is 1. Let's insert here. We see size of min heap is less than max heap. So let's pick that. Let's take the max element from max heap, which is 3. Let's put it back here. So we're going to insert here 3. What is the median up until this point in our stream? What is the median? Can you tell me? Alright, that's simple. Median is 3. I hope you're understanding. Let's move forward. 4, let's insert here. Now we see the minimum here 3. Let's remove, let's put it back here. Size is the same. Size of min heap is not less than max heap. So we will not remove from here and we will not put it back there. Okay? Let's move forward. This is our last element. Let's insert here. Let's remove the min. Min is minus 10. Let's put it back here. We see size of min heap is less than max heap. What are we going to do now? We're going to remove the max and we're going to put it back here. Now tell me the median. Can you tell me the median from this string? That is obvious. It is not difficult. Which is 3, the minimum from the right. I hope you are understanding. We are partitioning into 2 halves. On the left we have element less than the element on the right part. Okay? And we may have one more element on the right for the odd number of elements. This is how we can solve this question. Let me add one more number here. Let's add 20. So let's put it here 20. Let's remove the minimum 3. Let's put it here. Now what is the median? Can you tell me the median? On the left, what do you have? Minus 10, 1, 2, 3. Here what do you have? We have for median first we'll get 4, then 5, 6, 20. What is the median? It is the average of this. Max from right 4, min for left 3. I'm sorry, the minimum from right. Minimum from right we have mini data structure. So 4 plus max from left 3 divided by 2 equals to 3.5. Alright, this is how we can solve this question. This is the efficient algorithms. Now let's implement our algorithm. The most important thing in this algorithm is that we have to partition our given stream into 2 parts. Okay, we have to partition it into 2 parts. Now let's create our heap data structure first. I'm going to just write out the pseudocode, not the real code. If you need real code in your preferred programming language, please comment in this video. I'll share that. Now let's create here our heap data structure. Max equals to, this is our max heap. Min equals to, just curly brackets. Just think about it that this is our max heap and this is our min heap data structure. Now let's implement our insert method. Insert, it takes in is a number. We're going to insert in our data structure min heap and max heap. First, we're going to insert in our min heap. So min dot add this number itself. Now we're going to remove whatever the minimum we have in our min heap data structure. Let's remove that and let's add it back to our max heap. So max dot add. Let's remove from min heap data structure. So min dot pull. Alright, so we removed from minimum the peak element and we inserted in our max data structure. Now we're going to check the size. If we saw the size of min heap is less than the size of max heap, max dot size. In this case, what I am going to do, I'm going to remove the max element from max heap and let's put it back in our min heap data structure. Okay, let's do it. So max dot we have to add in min data structure, right? So min dot add. Let's pull from max dot pull. Our goal is to Our goal is to store the minimum element in our massive and maximum element in our min heap with equal symbol, or we may have one more element on the min heap than the massive. Okay, this is our core logic. If we go through a couple of examples, it will make sense. If you go through a couple of examples, it will make sense. This is a simple algorithm to solve this question. Okay, let's put here parenthesis. Now let's implement our find median function. That is easy. So find median. So first we're gonna check the length. Now let's sum the size of mean and maxive. So mean dot size plus max dot size. If we saw the size of min heap and max heap data structure, if we saw the size of min heap plus max heap modulus 2 equals to 0, it means, if this condition is true, it means that we have odd number of, if this is true, it means that we have even number of elements in our current string, or that is stored in our data structure. So here in that case, what I have to do, I have to find out the peak from max and peak from min, the root element. Okay, so here let's return that element. Return min dot peak plus max dot peak, and let's divide it by 2. This is the median. Okay, otherwise what we're going to return just the peak element from min heap, because in that case we have one extra element in the min heap. So you have to return the minimum. We have to return the minimum from this side, from the right side. Alright, so return min dot peak. This is our algorithm. This will take time complexity of 1 and space complexity of 1, and you clearly saw that. Peak operation takes a constant time complexity, and for insert operation it will take time complexity of log n for the verifying process, and it will take space complexity for n number of elements. It will take space complexity of n to store n number of elements in our heap data structure. I hope you've understood this video explanation. If you have any question, please post your question in the comment. And if you have any suggestions, please give me your suggestions, give me your feedbacks. If you think I have to improve the explanations as well as the presentations, please comment in this video. Thanks for watching this video. I'll see you very soon. Thank you.